All right, welcome everyone. Today, we're jumping into the cockpit to really get a handle on one of the most powerful tools in the entire data universe, Google BigQuery. If you've ever felt kind of lost in a sea of data or, been completely shocked by a cloud bill, then this one's for you. So let's kick things off with a scenario that I think is going to feel a little too real for a lot of you working with data at scale. You know the feeling. You run what you think is a pretty standard query, and then the bill shows up. And that's when you get that familiar sinking feeling in your stomach, right? You run a daily sales report. It seems simple enough. You're probably expecting, what, $10? But when the invoice hits your inbox, it's way, way higher. And you're just sitting there, staring at it, thinking, how did that happen? Well, here's the thing. The secret to BigQuery isn't just about what it can do. It's all about how you command it. See, if your systems are designed poorly, you can get these insane runaway costs. But today, we're going to unlock the blueprint to make BigQuery work for you, not against your budget. So let's get right to the most crucial point, the absolute core of this whole thing. BigQuery bills you for every single byte of data your query scans. It doesn't matter if your query returns one row or a million rows. It's all about the scan. This means your primary mission, your number one goal for keeping costs under control, has to be reducing the amount of data you scan, period. Okay, so to pilot this ship, you first got to understand how it's built. BigQuery's real secret sauce, its genius, is the total separation of compute from storage. Let's take a look under the hood at the core systems that make all of this possible. First up, you've got Colossus. The easiest way to think about it is like the giant cargo hold of our starship. It's this incredibly sophisticated, planetary-scale filing system. But here's the key. It stores your data in columns, not rows. And that's a huge deal, because it means when you query for just 2 columns out of 50, you only read those 2, not the whole table. Next, we've got Dremel. This is the engine room. When you send a query, Dremel basically unleashes this massive fleet of thousands of processing drones. These are the compute resources, and they all work in parallel to just blast through your commands at incredible speed. It pulls only the specific columns it needs from Colossus and gets right to work. So how do the engine and the cargo hold talk to each other without slowing down? I mean, moving petabytes of data is usually a massive bottleneck. Well, Google solved this with Jupyter. It's their own proprietary, ridiculously fast network that lets Dremel grab all that data from Colossus almost instantly. It's kind of the invisible magic that holds the whole thing together. And finally, there's Borg. Think of Borg as the ship's conductor or mission control. It's this brilliant master scheduling system that intelligently gives out compute resources, what they call slots, to thousands of different queries all at the same time. And the second your job is done, those resources are instantly freed up for the next person. It's incredibly efficient. Okay, so now that we get the basic design of the ship, let's learn how to actually navigate this thing. Our first big strategy is all about charting a really precise course through our data, and we do that using 2 super powerful tools, partitioning and clustering. So just imagine you have a sales table, and it's got 5 years of data in it. Let's say it's about 500 gigs. If you just ask for last week's sales without any of this smart navigation, your query just blindly scans the entire 500 gigabyte table. It's so inefficient, and you're paying for all of it. So here's how we fix that. It's a 2-step technique. First, we partition the table by date. Think of it like organizing a giant file cabinet into separate drawers for each day. Now, when you query for today, BigQuery only has to open today's drawer, scanning maybe 10 gigs. Next, we cluster by customer ID. This is like alphabetizing the files inside that one drawer. Now the query can jump directly to the right customer files, scanning a tiny 50 megabytes. And the result of combining these 2 simple techniques? It's honestly staggering. You get a 10,000 times reduction in the amount of data scanned. You get the exact same answer, but it costs a tiny fraction and runs way, way faster. That, right there, is the power of smart navigation. All right, next up, we have to talk about the blueprints for the data itself. Because in the world of analytics, some of those old rules of database design you learned, I'm looking at you, normalization, they don't just not apply, sometimes they can actually hurt you. See, in traditional databases, they teach you to normalize everything, to avoid duplicating data. You'd have an orders table, a customers table, and you join them. But in a distributed system like BigQuery, those joins are really expensive because data has to get shuffled all over the network. It's often way better to just denormalize and, duplicate the customer info right there in the orders table. The money you save from lightning-fast queries totally makes up for the slightly higher storage cost. But what if you could kind of get the best of both worlds? What if you could avoid massive duplication but still get rid of the joins? Well, you can. And the secret weapon is using BigQuery's native support for nested data structures. This basically means we can put a table inside of a row. Honestly, this is the new best practice. Instead of joining an orders table to an order items table, you can just nest an array of all the items directly inside each order row. This gives you perfect data locality. Everything about that order is stored together physically. No joins, no network shuffle, just pure, unadulterated speed. Okay, our architecture is sound, our data blueprints are in place. Now it's time to really master the commands that will turn you into an expert pilot. Let's dig into a few advanced SQL and caching tactics that can have a massive impact. This is such a simple rule, but it is so powerful. Always make your data smaller before you do an expensive operation. So don't join 2 billion row tables and then try to summarize them. No. Summarize each table down to 1 million rows first, and then join those small results. Shuffling 1 million rows across the network is cheap. Shuffling 1 billion rows is definitely not. Now, for those expensive queries that you run all the time, like the ones that power your main company dashboard, materialized views are an absolute game changer. It's basically a pre-calculated result that BigQuery caches and automatically keeps up to date for you. And the best part? Your users' queries don't even have to change. BigQuery is smart enough to just grab the answer from the cache automatically, giving you instant, cheap results. And finally, a pro tip: don't pay for perfect precision when a really good estimate is all you actually need. For quick data exploration or for dashboards, use BigQuery's approximate functions. They are often 10 times faster and cheaper. And for a lot of use cases, let's be honest, 99.99% accuracy is more than good enough. We've covered a ton of theory and tactics, so now it's time for your mission briefing. Here's a super actionable checklist you can take and use to start optimizing your BigQuery setup literally today. Here it is, your checklist. Go start by looking at your biggest and most expensive tables. Partition them by date. Cluster them by the columns you know you're always filtering on. Look for those opportunities to use nested structures and convert your most common heavy queries into materialized views. I promise you, just running through these steps is the fastest way to see a huge, dramatic impact on both cost and speed. By really understanding the architecture and applying these principles of smart design and efficient querying, you can completely transform BigQuery from this potential budget black hole into an incredibly powerful, predictable, and cost-effective engine for discovery. The data universe is vast, for sure, but now you have the tools to command it.